Okay, there we go. Now it seems to be working. Cool. Okay, so welcome back. Hope you all had a nice weekend. Everyone's relaxing. Maybe you went on a vacation or something. So today we're going to pick up where we left off. We have 2 lectures today, but they're both on the same topic, and I think we can fit them all pretty nicely within like roughly 2 hours we have allotted to us. So we can begin by going over the homework. So homework 5. So I'm giving you this table of directories and their paths, relative versus absolute, the working directories, and you have to create a tree out of this. So I guess, quick quiz, what is the difference between a relative and absolute path?
The relative path is given with respect to the working directory, whereas the absolute path is given with respect to like your root or the system.
Yeah, exactly. So relative paths are relative to the current working directory. Absolute paths are relative to the root, and they always begin with what? What do absolute paths always begin with? The // That's how you can easily tell at a glance. Okay, so yeah, question?
Maybe I get to think of this in terms of the path is, at least the working directory, as you would always go to, like if you're in the working directory and you hit CD and enter that, it'll go like that. That's what it'll work on.
Yeah, you could think of it that way. Assuming this is our whole file tree, you could think of it that way. So your classmate is saying that we could check whether or not the tree that we had made worked by using CDs to navigate to each of these paths from the given current working directory at each location. And I think that would work. The only perhaps issue you might have is that you might have to change some of your actual file tree to match this, which maybe you don't want to do. So, yeah. So to really explain this homework, I've actually prepared some slides here on the right to go through step by step what each of these steps would look like. So first is the home directory. This will just be, I'll give this one to start off, directly underneath the root, of course. Where would the dev directory be? Under the root as well, correct? And the boot directory, absolute path as well, also under the root. The first relative directory, where would the user directory go? Under the root, because it's relative to the root. Where would the directory Paul go? Okay. Does anyone know why it's Paul?
The previous.
Yeah, my advisor, Dr. Paul Gazzillo. So I just kept it with his name. So I feel like it's weird to name it after myself, so I just think I'd leave it with his name. Okay, so where does this long directory here go? /home, Paul, source.
Under Paul.
Okay, so we're relative to the dev directory. So we're going to start here, go up to the parent, because that's what 2 dots signify. Then we'll go into the home directory, and then Paul, and then underneath that Paul directory should be a new subdirectory called source, src. Where does this bin directory go? Underneath user, so user bin. Where does this bin directory go?
Under Paul.
It would be under home/Paul, so there it is. And then this extra home directory under Paul. So we're starting with the relative directory, the current working directory being home Paul, and we're creating a directory called home beneath this. So that would be right like that. And then finally, this directory Paul, where does this one go? This one's kind of a confusing one. Under what?
Under the second column.
Yeah, the one we had just created. So we start with a dev right here. We go up to the parent. That's what the 2 dots signify. We go down to home, then Paul, then home again, and finally we create the last subdirectory Paul. So any questions So you might be asked on an exam to do something like this, create a file tree given this listing of paths and the current working directories. Speaking of directories, I guess one extra thing that I'll show here, sort of just for your edification while we wait for more students to walk in. I found out recently that if you go into the man pages and type in man hire, it actually shows you a description of the file system hierarchy, what you can expect a standard Unix file system to have at certain locations within your directory tree. So for instance, the slash, it tells you, is the root directory. This is where the whole tree starts. And you can kind of get an idea of what conventions a typical Unix machine will follow when naming its directories. So we can see /bin is for executable programs which are needed in a single user mode and to bring the system up or repair it. These are not applications that a user would install. These are ones that are specific to the system for it to run and maybe repair any issues that are going on. So I think this is just interesting to note because you'll see many machines follow these conventions. And it's kind of a long list. So maybe you don't need to read all of it. Maybe skip the subdirectories, but the top level directories are probably pretty useful to like review, but not essential for this course. Okay. Now it's just to pass a little bit of time. So today we can start going over syscalls. So any questions before I begin? Okay. So I want to begin by reviewing what we had already seen in the first day of this lecture, or first lecture of this course, I should say, first day of this course, and that is defining system software. So can anyone tell me in their own words what system software is, if you remember, based off the first day's definition? A bit more, hopefully, than what was listed on the slide, maybe a more comprehensive definition. Yeah?
The layer that it glues our inputs to the programs that we're trying to use, and maybe not our inputs, but the hardware that we're using to accomplish those things.
Okay, and what does system software typically interact with in order to interface with the hardware? What is that layer below system software?
Kernel?
The kernel, right? So, see that on the next slide. If user applications like web browsers and video editing software, or maybe programming languages are at the top, system software is between applications in the kernel, where at the bottom, lowest level is the hardware, where we have different sorts of hardware devices like CPUs, motherboards, hard disks, solid-state drives. What's important to note is that all these different kinds of hardware have different specifications and timing specifications for how data should be written and read from each of these devices. And that's a problem because we have all different kinds of hardware devices that we're trying to interface with, and there's a diversity even within certain classes of hardware. So you can think like solid-state drives. I don't know how many of you are into PC building or into computer architecture at all, but there's now like diversification within that as well. We have NVMe drives, SATA drives, and all this means is that we can't just use one method of writing bytes and reading bytes from a location, to and from a location. We need to have different support for different ways of doing this for every single kind of device. I guess another quick quiz. What is the abstraction for reading and writing bytes to and from a location? We saw this in our previous lecture. A file, right? Yeah, you're right. So a file is the abstraction for reading and writing bytes. So even though we have this abstraction, a file for reading and writing bytes, that the way we actually do that might differ for a flash drive versus a solid-state drive versus a hard drive for a different manufacturer. Bless you. And so the kernel exists to bridge that gap for us by sort of adapting, providing like these adapting any ways we want to, or providing abstractions for us, I should say, to write to this hardware. And the interface that exposes for us to do this is called syscalls, or system calls. Yeah, so again, the kernel allows us to abstract away these hardware differences, but there's some other benefits here. Being able to share hardware resources. So this is what enables us to all log into Eustace and use the same machine. This sharing of hardware resources, we are all able to have multiple users. And you can also, for this, the sharing of hardware resources also enables us to do what's called time sharing, where we can run multiple processes at the same time, and we have this illusion of concurrency. Multiple processes are never actually running, well, by processes I mean running programs. They're not actually running at the exact same time on your machine, but we have this illusion that they are because the kernel is able to schedule these tasks, these processes, to run at different times, so that there's never really a delay in processing for you as a user. You just see them all running at what appears to be simultaneously. And then, of course, there's security measures. So again, we're all logging into Eustace, but none of us have direct access to other users' directories or direct access to memory, because that would be bad. You can maybe tamper with another student's assignment or even copy it. So the kernel provides ways to protect against all this with user permissions and so on. Yeah.
What exactly is it wrong? Because I tried to Google it, but it was just starting.
So there's kind of a joke here that I'll use to explain this later in the course and show it. But does anyone know the actual definition of a kernel, like the dictionary definition of the word kernel? Okay, so a kernel is the inside of some kind of nut, I guess, or berry. And what is the tool we're using on the command line to interact with the kernel? What is that called?
Shell.
The shell. So the kernel is what's inside the shell. Yeah.
Were they named in that order? Like, they named the shell first?
I'm not actually sure what came first. Yeah, so we use the shell to interact with the kernel, which is closer to the machine. That's the big idea. That's why it's called the kernel. Yeah, it's kind of a joke. At least I think of it as like a joke. Okay, so let me actually illustrate this now with this diagram. So again, what you might think happens, so the way, okay, I guess one more thing to point out here is that the way the kernel implements a sort of abstraction and also security measures is through this notion of user space versus kernel space. User space has restricted permissions on what it can do. Kernel space has basically free range to access hardware and read and write bytes to and from it as necessary. And when we read and write bytes to different storage mediums, what you might think happens is that our reads to those different devices go directly to those specific devices. So you might think, like, if I'm reading a file or writing a file to a hard drive or to a USB stick, it goes directly to these different devices. But again, that's not really what happens. What really happens is that under the hood, the software you're interacting with, let me fill this with black here, is actually talking to some sort of black box inside the kernel. I'm just going to depict this as a black box because the way this actually works is not really important to us. The kernel has its own, the implementation of the kernel is not really something that we're concerned with in this course. What we're more concerned with is the fact that inside the kernel there are these so-called drivers. Oops, let me fix this, there we go. Drivers, which we can think of as like black boxes, which abstract away the differences between these different media for us, for reading and writing bytes to and from them. So when you try to read a file from a hard disk, that makes what's called a system call to the kernel, which goes into kernel space to actually perform the necessary actions to read bytes from that file. And there's another driver for interacting with USB sticks, for instance. Yeah?
When you say space, are we talking about like a permissions abstraction or like a reserved area of our storage?
It's not, it's more like a permissions abstraction thing. Or maybe like a mode, I guess you could say. I mean, to know the exact difference, you'd have to take an operating systems course. That's kind of beyond the scope of this course, unfortunately. We're not going to be going into too much detail on user versus kernel space. What's important to know here is that we're not accessing these files, these devices directly. We're going through the kernel to access these devices. And the interface we're using to cross this boundary is syscalls, system calls, which I'll be giving you tons of examples of them throughout the rest of this lecture. one more cool thing here is that if you wanted to, because the kernel is open source, you could add your own driver. So if you wanted to add support for Linux for interacting with VR headsets, for instance, this is what I've drawn here, or put an icon of here, I didn't draw that. You could just add your own driver and make a request to have it merged into the kernel, and if it gets approved, then you contribute it to the Linux kernel, and now millions of devices around the world can potentially interact with that VR headset. So it's a good starting point for adding to the kernel to add new drivers to it. And a long time ago, like a few decades ago, Linux was not really practical to use because it lacked many of these drivers. It couldn't interact with a lot of different pieces of hardware. But nowadays, it's not really a problem, not as much of a problem. There are many more drivers on Linux for interacting with all different kinds of hardware. Okay, so any questions? Okay. So again, what I'll say here is that the kernel exposes, that's the word you commonly see used, exposes this interface for interacting with the hardware, and this interface is called Syscalls. And I guess to illustrate this again in a different way, has anyone been doing the reading? Anyone? I recommend reading the book. It is a good book. I haven't read all the chapters, but I was reading several of them when I was a TA for this course, and they're pretty easy to read and actually very informative. So I have a diagram here from the book that I want to highlight. We can actually, so these syscalls that I'm talking about, they are available to us from within C code. So we can actually write C code to invoke, that's the word used, invoke these syscalls, and they look like regular C functions in order to enter user mode and then, or kernel mode I should say, and perform some sort of kernel abstraction, whether it be reading or writing bytes or doing something else. And the example that they have in the book, which I think is really helpful, is how in some user application, so this could be C code that we wrote, you might have this call to this syscall execve, which we'll see what this does later in the course. When this syscall is made, execution will flow into this glibc wrapper function. So glibc is the GNU implementation of the C standard library. So GNU is the same organization that makes GCC, the GNU compiler collection. They also have their implementation of the C standard library. And in this wrapper function, what it basically will do is set up some variables and put some values into memory at the correct locations before executing this syscall instruction using what's called a software interrupt, specifically a trap. And a trap or a software interrupt is what's used to enter a kernel space. So the kernel will recognize this specific kind of software interrupt, look at the number that was passed for that interrupt, and then perform the appropriate system call. And it does this through this trap handler. So the trap handler will see that a trap was executed, and then use the number passed to execute the appropriate system call in the kernel's implementation itself. And the kernel is implemented in C, but this is basically assembly code here, actually. So the kernel's implementation of this system call will execute. It'll probably do something different depending on the hardware that it's interacting with and that your system is running on. And then when it's done, control will eventually flow all the way back up to the application program back into user space. So under the hood, that's what's going on. Most glibc function, most syscalls we're going to be executing actually don't execute the system calls directly. They first go through some kind of thin wrapper function that just sets some variables up in the correct locations in memory into registers and whatnot in order to execute the system call. So any questions with this diagram? Again, you don't need to know too much of the details of this. This is just sort of giving you a high-level overview of what's going on with syscalls. Okay. Yeah, so again, syscalls, just like C functions, we'll see them shortly. And you can run man syscalls to get a list of all the syscalls available to us. So this is going to be in section 2 of the manual pages. I'll review the sections again shortly. But if we scroll down here, you can or see in the description, the system call is the fundamental interface between an application and the Linux kernel. So that kind of just backs up what we've been saying, the way to interact with the kernel itself. System calls are generally not invoked directly, but rather via wrapper functions in glibc. So that matches what the diagram that we just saw showed. Often, but not always, the name of the wrapper function is the same as the name of the system call. Often the glibc wrapper function is quite thin, doing little work other than copying arguments to the right registers before invoking the system call. And then setting error no appropriately after the system call is returned. So we'll see what error no is later in this lecture. And the body of this man page section, or man page here, is just a list of all the different system calls. So you can go through this and peruse all these. You can actually see this number here next to each name. Tells you what section of the manual page each system call is under. They should all be under number 2, because number 2 is for syscalls. And all of these we can actually view the information for by just using the appropriate man page. So again, like this word select here, this is a syscall. We should have a man page for it, and we do. So I'll show you how to read those syscall pages, the man pages for each syscall, soon we get to an example. And again, just I guess to illustrate what those numbers mean, if I go to the manual pages for man itself, we have this description of all the different sections of the manual, section numbers of the manual. So 1 is for executables, 2 is for syscalls, 3 is for library calls. These are functions provided to us by the C standard library, but they're not tied to the kernel itself. And there's more. 7 is for miscellaneous. So that one I showed you earlier, man, HIER, is number 7, so it would be under the miscellaneous category. And knowing the section numbers is useful because there are some syscalls which share a name with binaries. So for instance, man open, if I run man open, that will by default open the man page for this binary xdg open. Which is not maybe what I want. I might want to get the manual pages for the syscall open. So I can say man2 open, and that gives me the manual pages for the syscall open. So we'll see that one again later in this lecture, but just to show you now, there's a reason why it's important to know the difference between the different sections in the manual pages. It's not just a fun factoid, it's actually useful when you're trying to access and disambiguate different pages, different sections of the manual. So there are some library calls. Let's see here. Yeah. So I don't know. Have you all seen these library calls before? fopen, fprintf, fscanf. Yeah. Has anyone not seen them? I feel like these are pretty common. You probably reviewed these in Intro to C, in CS1. And these are like nice abstractions for us to interact with files. So these all return file pointers, right? Which are somewhat easy to work with for C standards. They're pretty easy to work with. But there's a lower level variant for each of these, lower level counterpart. And these are the syscall counterparts. Man2 open, write, read. These interact with file descriptors, which as we'll see are a bit lower level, a bit closer to the machine than file pointers. They don't provide some of the niceties that these higher level abstractions do. For instance, with the write syscall, we don't have access to format specifiers for printing our output real nicely. We can't use %d, we can't use %s, %c, etc. We have to just write bytes directly to a file with the write syscall. And let's see here. Yeah, all right, so I think it's time. Yeah, this should be good. I'm not going to go over this in the slides. I think what I'll do instead is just start going over examples now. And I think that'll be a lot more engaging than the slides. So let's begin by going over a simple syscall. So first, I guess I'll list the contents of my directory. I have a bunch of different files here, C files, that we're going to go over. Each one demonstrates a different syscall and how to use it. So it's sort of in the way. I'll just put this back here, I guess. Okay, so the first one that I want to look at, oh, and I have a makefile also that will let me just quickly compile these C files to binary so we can run them and test them out. So the first one we're going to look at is open simple. And we're going to be looking at the open syscall. So open is right here. I'll go to the man pages for it. Oops. This is the manual section 1. So what can I do to get to the manual pages for section 2? What can I type?
Man to open.
Man to open, yeah. So I showed that earlier. So the way you can read these man pages for each syscall is that it tells you the name, and then it tells you what includes are necessary to use that syscall. So in this case, we need the fcntl file control header in order to access the open syscall. And the description for open says the open syscall opens a specified file specified by path name. So path name is right here. That's the first argument. If the specified file does not exist, it may be optionally, if O create is specified in flags, be created by open. So to demonstrate this, in this C function here, this main function, we are assigning a variable path to the string hello, and then we're calling open, and we are assigning, as the first argument to open, passing, I should say, the path argument here. So we're opening the path hello. Our second argument is a bit mask. So does anyone remember bit masks from CS1? Can someone describe them for me? Yeah.
So they're using so we're using bitwise operators to extract individual bits from a sequence. So like for instance, if we had like 2, or if we had like 4, but we wanted to just extract if it's even or odd, we could use the bitwise AND operator.
Yeah. So not just extract, but also combine, right? We can create our own bit masks. So as your classmate is saying, if we have a binary value like this and one like this, we could OR these two values together to create a bit mask that looks like this. And the reason why I want to do this is because it lets you compactly pass a sequence of binary flags all in one argument to a function. So it's a way to quickly combine different binary values all into one. So you can think maybe this bit says we can open the file, we can read a file, this bit says we can write a file, you OR them together and you get read-write permissions all in one. Just as an, I don't know, arbitrary example. So for this bit mask, the second argument here, we're passing the flags to open. The first one we're passing is O write only. So let me actually delete all this for now. I'm going to delete all this, make this a bit simpler. Yeah, I think maybe I should delete all this to start off with. So we're going to open this file. We want to open it for writing. We want to write to this file hello. And according to, oops, let me zoom in again. The man pages, is this big enough? Yeah, okay. We have these flags available to us. The full list of file creation flags and file status flags is as follows. Actually, first let me go back up to the description here. Right here. The argument flags must include one of the following access modes: read-only, write-only, or read-write. These request opening the file for read-only, write-only, or read-write respectively. So if we want to open a file for writing, we would pass O write-only as the first flag. Now if I ls the contents of my current directory, you'll see that the file hello does not currently exist. So we need to tell the open syscall to create that file if it doesn't already exist. And the way we do that is with the O create flag. If the path name does not exist, create it as a regular file. So we can combine that with the O write only flag by ORing it with it, ORing the bit mask with O write only. So now we're saying open the path, the file at the path hello, and open it for writing and create it if it does not exist. So if we run this, I'll say make, make open simple. Then I'll run this here. And then if I list the contents of my current directory, you'll see the hello file now exists. Now there's nothing in it. We didn't write anything to the file, but we did create it. Now you'll commonly see paired with oCreate is another flag oTrunk. What trunk does, if the file already exists and is a regular file and the access mode allows writing, i.e. is read-write or write-only, it will be truncated to length 0. So what that means is that the file's length is set to 0. So when you start writing, you essentially delete everything in the file first and then start writing from there, from the beginning of the file. If we don't specify oTrunk, then we'll just start overwriting. If we try to write bytes to this file, we'll just overwrite the first however many bytes that we write without actually deleting the contents of the file first. So, yeah. Okay. Now, one more thing I want to point out here that's sort of a pitfall with, yeah, see how it says this? With open, is that if we're creating a file, does anyone remember how I mentioned before that files have access permissions? So there's different permissions. There's user permissions, group permissions, other permissions. And when we create a file, we need to provide those permissions for a newly created file. And in this case, we're not doing that. We forgot the argument that does that. So what happens is this file is created with arbitrary permissions, and the permissions that it was given just happen to exclude write permissions. So I can't just delete it without a prompt first. So I'll say yes to delete it. And the way we can fix this, to add permissions to this file, is to specify the user permissions for this file using different flags as well. So right here, the following symbolic constants are provided for mode. So this is underneath the oCreate flag. It tells us at the top of the thing here you can see there's these optional mode argument. If oCreate is specified, then you have to provide as well a bit mask for the permissions of this file. So we can give the file user read, write, and execute permissions with irwx, u. We probably don't want execute permissions because it's just a text file. We'll give it user read permissions and user write permissions. The way we can do that is by ORing these two bit masks together. Now if I run this again, so, oops, I'll do open simple. The hello file exists, and I can remove it, and there's no warning because the file permissions were specified as we set them to be. So again, I'll run this again. Sorry, the stat syscall. And we can see we have read-write permissions for the user on this file, which matches the exact permissions that we specify here on the left. So any questions so far? Yeah.
What's the dash or hyphen 0400?
Oh, 0400. Where is that?
Like all the way, like access all the way to the right. Yeah.
Oh, that's just the time zone offset.
Okay.
Yeah, these are access times. This is the last time the file was accessed, the last time it was modified, the last time its status was changed, and when the file was created. This is just a specification of the time in military time. And then the negative 0400 is the offset for Eastern Standard Time. Yeah, good question. Okay, so one more thing that we should be doing here that we really need to do whenever we make a syscall. Actually, what I'm going to do is close this here and keep the main pages open on the right now. Whenever we use a syscall, we need to check two things, which is the return value. That's the first thing. And it says on success, open, and its other variants, return the new file descriptor, a non-negative integer. On error, -1 is returned and error no is set to indicate the error. So what we need to do is store this file descriptor, which is going to be an int because the man pages specify that it returns an int. We'll say int fd for file descriptor equals this call to open. And a file descriptor, the way you can think of it, is just a unique ID for a file. It's not a file pointer, it's just a number that references a specific file. A lot of syscalls interact with files using these file descriptors instead of file pointers or file names. They return and take as input these integers that are IDs identifying different files. Okay, so back to the return value. So it says on error -1 is returned, so we can check for an error by saying if -1 is equal to fd, then we'll say fprintf, standard error, error opening %s, and error no is set to indicate the error. So what is error no? Let's open up the man pages for error no. So error no is the number of the last error. So every time, this is something you'll see with syscalls, and to be honest, I kind of hate this interface, but it makes sense why they did this. Every time a syscall throws an error, it will exit with usually a -1, maybe sometimes another value, or a null value. And then it will set the global variable error no to a special number that represents whatever error was thrown. So what you'll often see with syscalls is something like this, where we check the value of error no. So we'll say -1 is equal to fd, and then we'll just print the value of error no here. And then exit early because we had an error. We could also exit using the exit function, but instead we'll just return early because we're in main, so we can just return 1. So I'll run make again. Oops, I forgot to pass the specifier for the path that we're opening. So that will be path. Okay, so it ran without an error. Let's say we wanted to open this file. I guess one error we could do. I'm going to try and add an error here just so we get this error message. Let's say read only. So we're not writing, we're reading a file. And I'm going to remove that hello binary so the file doesn't exist. And now if I run, got to recompile it. If I run open simple, we get the error message, error opening hello, number 2. So presumably the number 2 corresponds to the error for a file not existing. So does anyone see any obvious problem with this approach of handling errors and printing them out?
You can't really know what the error is.
Yeah, we'd have to memorize what every single number, what error each number corresponds to, which is really ridiculous. We shouldn't have to do that. And I think in the manual pages for error no, there actually is a listing of every single error and what number they correspond to. And these are all provided as symbolic constants, so you could actually type this into your code, into your C code, and it would actually correspond to the appropriate number. But we shouldn't have to remember what all these mean. And C developers realized this is a problem a long time ago, so this is where we have the next thing in the slide here, using p-error. So we're going to use this library call. So set manual page section 3 for library functions. These are ones that the C standard library provides to us, but which are not a system call. And p-error prints a system error message. It'll basically just interpret the value of error no and then print it out. So it produces a message on standard error describing the last error encountered during a call to a system or library function. Okay, so the way you would actually use p-error in practice is usually like this. You call p-error, and you pass the name of the syscall that you just made, which failed. So we would say p-error open. And now if I run make, and then run open simple again, you can see it says open no such file or directory. We get a much cleaner error message this way. And you're going to see this a lot throughout this course as we use syscalls. This is like the standard approach to using them is you make the syscall, you check the return value. If it's a failing value, then you just p error and then exit early. If you're in another function, maybe return early. Or you can just call exit to exit the whole program early. Okay, so any questions? Yeah.
So if open gets an error, it'll return the -1.
Yes, and this is, again, specified in the manual pages for open. You can search for return value, all caps, and all the syscalls have this section that tells you what they return. So you know what to check for. It'll usually be -1. Sometimes it's null, sometimes it's something else, but usually it's -1. And you can also see there's this error section here, which tells you the exact error numbers that error node could be set to on failure. So if you want to have an exception, maybe you don't want to throw an error if there was no file found, you want to instead do something else, then you can actually check the value of error node to see if that's the case. So I could actually say if e no ent, which I believe is down here, right here, e no ent. A directory component and path name does not exist, or is a dangling symbolic link, which means that just the file does not exist. I could actually check that by saying if enoent is equal to errno. Then instead I could say fprintf file does not exist. And then let me recompile and run that again. No, standard error. And you'll see now we get the error message file does not exist. So, and sometimes you'll actually have to check the value of errno to see whether or not a syscall has failed, or you'll have to set errno yourself. We'll see that later in this course. There's a few different cases where that might be the case. Okay, any more questions? All right, one last thing that I want to show that I've learned about recently that's kind of cool, that's related to all of this, is the error library call, which is kind of like p-error combined with the return statement. So what error does, ERR, they display a formatted error message in the standard output, and then, let's see, they do not return but exit with the value of the argument eval. So the way you would use this is instead of saying p-error open and then returning 1, you could say errno open. Oops, let me fix that. This is in the error header, so I'll include that up here. Add that comma, maybe missing it. And now if I run open simple, it actually does the same thing, except now it actually tells me the name of the program that had the error as well, and it exits early without me needing to call exit 1. So I can actually check the return code of that program, the exit code of that program, by echoing the $? This is the special variable that bash creates for you that tells you the exit code of the last executed program. And we can see that it's 2, which, as we saw earlier, was the value that errno is set to when no file is found. So sometimes this is useful as like a shortcut, but I'd recommend for this course, if you just want to keep things simple, just use p-error. It's pretty simple to use. Okay, any other questions? Any questions? Okay, let me check one more thing here. I had a bigger example. Let me see what's in this one. Yeah, so this one's a little bit different. Yeah, okay. So in this case, we are not just opening the file, we're accepting an argument with this program. This is open complete, so in this one, we can actually specify the name of the program that we want to read from. And then what we'll do is call another syscall close, which simply closes a file descriptor, so that no longer refers to any file may be reused. So, you've probably seen fclose to close a file that's been opened with fopen. Similarly, there's close for closing a file opened with open. So don't forget to close your files. We didn't do it in the last example. I wanted to keep it focused on the open syscall. But here, in this complete example, we would close the file with close. So if I wanted to run this here, I could actually pass call open complete, and if I run it with no arguments, it will actually print this usage message saying that we need to pass it a file. That's what these 3 lines of code up here do. They check argc, so argc is the number of arguments passed to the program. If it's less than 2, that means no arguments were passed, because the first implicit argument of any program is the name of the program itself as it was ran on the command line. So if we were to run this here, and I'll actually pass OpenComplete's source code to OpenComplete, we get the message of success, indicating that we were able to open the file, close it, and then print the success message. Okay, so I think that's a pretty gentle introduction to a basic syscall, open. We're going to see more of them throughout the rest of this lecture, all different kinds. But for now, I think maybe it's a good time to take a break. So I'm going to leave this open on the screen here. And actually, no, I'm going to open up UCF here. Stop recording for now. So a student had asked about software engineering here at UCF. It's taught by this professor here, Dr. Moran. This university, he's a newer faculty member here at UCF. He's a very good person to talk with, very, very competent professor, very good researcher. He's won awards. He teaches, software engineering, CEN 516. So I'm not sure how many 5,000 level courses you can take as an undergrad, but that's one of the courses I would recommend taking. The other one would be compilers with Dr. Gazillo, my advisor. That's if you like the first half of this course more, take software engineering. If you like the second half of the course more, take compilers. That's 50, 60, 21, I think, or something. 50, 61. Yeah, I'll go over that one more when we get to the second half of the course. I just realized my microphone was not on. Okay. So we should be good now. I'm recording. And we can go back to talking about syscalls. All right, so the next syscall that I want to talk about is stat. So does anyone remember what the stat program does? I just used it earlier. The command we can run from the command line, stat. What does it print out?
A bunch of timestamps of when it was accessed and permissions.
So that's some of the information it prints. Yeah, it prints file access times, modification times.
The file number?
The file inode number? Yeah, prints that. It also prints file size, so we can say stat, dot, the current directory. So all directories are 4 bytes in size, but this is information about it, the number of blocks, which is like a unit of storage on the kernel, it's specific to the kernel. The file type, the number of hard links to this file. There's also, let's see, I can run stat on that example we saw, the code we were looking at earlier, opensimple.c. The number of bytes this file has, 248, it's a regular file. Access times, modify times, change times, worth times, etc. What's cool to note here is that stat, if we run man stat, we open up the man pages for the stat command, but if I say man to stat, you'll see that stat is also a syscall. So the way the stat command gets all that information that it returns to us is through the stat syscall. So what we can do is actually access this information in our C programs directly using the stat syscall. And we're going to be using this syscall in one of the upcoming assignments called MyFind, where you're going to be tasked with navigating the directory tree and printing out some information about different files, their size, the number of directory entries a directory has, etc. So I'd recommend practicing the stat syscall, and we're going to go over it here now. So let's open up this file, file stats.c. So in this program, we're setting up a variable path and declaring this variable called statbuff, which is of the stat type. We'll see what that is shortly. That's necessary for using the stat syscall. You know, I'm going to move this because I can't look at you when I don't have this in the way. So I'll do this. Okay. If the user passes the correct number of arguments, then we assign the first argument, or assign path to the first argument passed. And then we call the stat syscall on that argument, passing the stat buff to it. So what does stat do? Well, now here's a cool thing. In Vim, if I press capital K on a word, it will open the man pages for that word immediately. And you can see it opens the wrong man page because, as we saw earlier, stat is both a command and a syscall. So if I press 2 and then capital K, it will actually open the manual page section 2 for that word. So I don't have to leave Vim. I can stay in Vim and quickly access man pages. So we can see the stat syscall requires us to include the sys/stat.h header. It expects one argument, a path name. This is a char star. The restrict keyword, what that basically means is that we don't have two pointers pointing to the same value. This is so we can perform compiler optimizations. You don't really need to know what this means for this course, just in case you're wondering. It's really just to signify that we can perform some optimizations on this function. And this stat buff struct is the second argument. So how does stat work? Let's read the description. These functions, so all these stat functions up here, return information about a file and the buffer pointed to by statbuff. So we're returning our result of this stat syscall in that statbuff argument we pass into the function. And what does that stat buff look like? Well, it says here, all these system calls return a stat structure, cstat3 type. So if I go to manual page section 3 for stat, it will actually go to the manual pages for the stat struct. And let's just check the return value. On success, 0 is returned. On error, -1 is returned, and error no is set to indicate the error. So that's why in the code here, I'm checking for -1 to see if an error occurred, and then if an error did occur, I'm using the same pattern of p-error stat and then exit 1. And the stat buff, so we're passing a value by pointer. We're passing the stat buff to the stat struct. Why are we using the ampersand operator here? What does that do? Not dereference, but reference, to get a reference. Yeah, close. So we're getting the address. We're getting the address of stat buff. So that way the stat syscall internally, presumably, can dereference that pointer and set the appropriate field values in that struct to whatever the result of the stat call is. So what does this stat buff actually look like? What fields are available to us? Well, I can press 3 and capital K to go to the type for the manual page for section 3 for stat. And we can see this struct provides all these fields. We have the mode, which is like the file type and its permissions. So that's what mode has, the permissions. The number of links, number of hard links to the file, the user ID of the owner, the size of the file in bytes, all sorts of stuff. The inode number, or actually no, right here, the inode number of the file. So all this is given to us. There's also some useful fields here, access time, modify time, status change times. And I've actually used these, like I mentioned earlier in research. I had to write a program to actually track what files a given command modified. So I actually used the stat syscall to write a C program that would get the last access times of every program, every file in a directory, run this given command, and then compare the last access times after running that command to the before times, and if there was any difference, you could record it as a file access. And using that, I was actually able to write a whole paper. So it was pretty cool. So this stuff does have like applications. Yeah, and you can see there's a description of all these different fields down here. So for us, we can just print these fields as shown. Let me actually, yeah, I'll delete this. So if we want to print the file size, we just say, for instance, statbuff.st_size. And if we go back to the stat man page here, we can see that st size is this offset underscore t type. So I think there might be man pages for this. Let me check. Man off t. Yeah, right here. File sizes. They're used for describing file sizes. It is assigned integer type. We don't know the exact size of this integer type though. So instead of using %d alone, we use the %jd specifier. That says go up to the maximum size permissible for integers. This is something that you have in like later versions of the C standard, like C99, so all C compilers by today should have access to this format specifier. But if you see this %jd and are wondering what the J is, it's just necessary for using these special integer types that the statbuff struct exposes to us. Because we don't know the size of these integers. It depends on your platform. So this is just for sort of a compatibility thing. We can get the number of hard links as well with stnlink. So why don't we try actually using this? So I'm going to run make. And I'll run this file stats binary on itself. And we can see it says file size is 482, number of hard links is 1. And if I run stat on the file stats.c file, we can see that the stat command, its output seems to match the output of our program that we just wrote. So number of links is 1 and size is 482. That seems to match what we have up here as well. So something else worth knowing how to do with stat is getting the type of the file that you have just called stat on. So this could be a directory, it could be a regular file, it could be a device file, it could be some other kind of file. There's several different kinds. And the way we can do this, I'm going to check this here, man3 stat, let's say, open the man pages here again, 3 stat, file type and mode, st mode. If we go to the man pages for st mode, or search for st mode in the man pages for the stat struct, it tells us that we have to look at inode 7 for further information. So let's do that now. I'll say man 7 inode. It tells us more about the file inode information, and what's important on this page is that down here it tells us how we can actually access check the file type of a file. So we can say, for instance, they give us an example. If you call stat on some path name and want to check whether it's a regular file, you can actually do some bit masking operations here on the format with the mode and this format bit mask to check whether or not this is a regular file. So we can do this like this. I'll just copy this here. So what we're doing is, so the st mode field contains the file's type, but also its mode, the permissions of the file, all in the same field. So to extract the file type information, we have to AND it with this bit mask here, si_format. And then we're checking against another bit mask value. Is it a regular file? And if it is, we can just say printf regular file. Now we can try running this. Oh, sorry. This should be statbuff. What I'll do is actually open this below so we can read the whole C program. File stats.c, and now it says regular file. Now this is kind of like onerous to write all this ANDing with this bit mask. So to make it a little bit easier, we have this other macro that's provided to us. I'll open it here for us. Man7 inode. Oops, man7 inode. we can see that there's all these macros, which macros are just named code fragments. They're not really functions. They're just they're expanded when the compiler runs in your C code into a corresponding block of code. This will actually just do this above check for us. So this actually will expand to what we have up here. So we can just replace this with s underscore is reg, statbuff, dot st mode. I think that's how you'd use it. Now if I run make, oh, oops, let me get rid of this part. Yeah. There we go. You can see it works the same as before. So if you want to check if a file's type, you can do it a little more easily by using these macros. And there's one of them for each kind of file, each kind of type that a file could have. Now, one other cool thing you can do that's even more, I'd say, versatile or comprehensive, covering all cases, is instead of saying if, and I'm showing you this because it could be useful for your project coming up, is to use a switch statement here. Statbuff st mode and s underscore I format. And now we've extracted with this ampersand here, since with this and, we've extracted the format bits, or the file type bits of this st mode field. And now we can actually create different case labels for handling each one of those different file types. So the way we can do this, I'm going to open this up on the right here. Command 7 inode. We can see there are all these different file types listed in the documentation. Now I'm going to use this as an excuse to kind of show off some of the reasons to use Vim. I'm going to be doing a little bit of editing here. So I can just copy this directly. I can paste this in. Now I can press Control V to enter visual block mode, and then select all these characters, press X to delete them all. Delete all these lines. Visual block mode, case, go to the end again. Select all that. Select all those. Paste them all back in. Actually, we'll do it like that. And then finally, at the end of each of these statements here, we'll just say break. And in the default case, we'll just say unknown file type. Do we need a break statement at the default case of a case label? No, right? Because there's no other cases to follow through to, so we don't need a break statement. And assuming I typed this correctly, I didn't make any typos or made any egregious mistakes, this should just work. So now I can say make, yep, didn't get any issues. And if I run file stats on the filestats.c file, you can see it actually says a regular file, s underscore ifreg, which is what we have here for that case, which corresponds to a regular file. If I pass the current working directory to it, it will say ifdir. So you might want to use an approach like this, where you use a switch case label to handle different kinds of files in your MyFine project coming up. You only have to handle regular files and directory files, so maybe not, but it's kind of cool to know how to do this, I think. Also, just showing you how you can use shortcuts in Vim to quickly edit a whole bunch of text and copy and paste things over. So it's sort of an incentive for you to maybe consider learning Vim. Okay, so any questions on the stats Syscall? Okay, so we'll move on to the next syscall then. Series of syscalls, reading files. So we already saw open, I think. Oops, not man, them. Yeah, so we already saw open. Let's see, what was the next one we want to look at here? Let me run make clean. Let's look at read. So I'll put this, yeah. Okay, I'll delete that for now. So the read syscall, as the name suggests, reads bytes from a file descriptor. So with the open syscall, we can open a file. With the read syscall, we can actually read bytes from that file and store them into a buffer given as an argument to read. So read is a bit lower level than, so I'm gonna, let me ask actually, what's the library call, the equivalent that we would use for reading user input? What do you normally use to read user input from standard name? Scanf, right? Scanf, or what else? What did somebody else say? Fread, you could use that too, read from a file. Fdisk, yeah. For those library calls, do you need to specify the number of bytes you're reading? No, right? It's a bit more, well, the abstraction's easier to use. For read, however, we actually have to, let me open this again, we have to specify the number of bytes we actually want to read from the file. So it's a bit lower level, a bit not as, I guess, easy to work with, but it's a more precise tool. This also opens the door to vulnerabilities. If you accidentally read more bytes than you were trying to, you could open yourself up to some kind of cybersecurity attack. So, okay, so read attempts to read up to count bytes from the file descriptor FD into the buffer starting at buff. On files that support seeking, the read operation commences at the file offset. So we can actually say what location in the file we want to start reading from, but if we don't specify that, we'll assume the beginning of the file. Okay. Let's see, return value. On success, the number of bytes read is returned, 0 indicates the end of the file, and the file position is advanced by this number. It is not an error if the number is smaller than the number of bytes required or requested. This may happen, for example, because fewer bytes are actually available right now. So if the file is only 20 bytes in size and we request 32 bytes, we might only get 20 bytes back, and that's not an error because the file only had 20 bytes in it. Or because read was interrupted by a signal, so we'll talk more about signals later. Signals are a way for processes running programs to communicate with each other. On error, -1 is returned, and error no is set to indicate the error. In this case, it is left unspecified whether the file position, if any, changes. So we can actually keep track of the number of bytes that we have read because from the return value of read. So read returns number of bytes read. So I have this buffer declared up here, buff. We're going to try and read 32 bytes into buff. And we're going to store the result in this bytes read variable. So bytes read is a size type, but it's a signed size type. That's what the S stands for. And the reason why we use a signed size type for the return value of read is because read can return -1, and -1 is a signed value. So in order to support that error value, we need to have this return type be a signed size type. So now we'll execute the read syscall, invoke the read syscall. So we'll say if -1 is equal to read. And let's look back at the man pages. The first argument is the file descriptor, which we got from open. That should be FD. The second argument is the buffer we're reading into. So we'll say buff. That's going to be right here. And the third argument is going to be the number of bytes we want to read. We'll use count number of bytes. So we'll just say count. And if it's equal to -1, that means there's an error. So what should we do in this case if there's an error? P error, right? P error, read, and then we can exit 1 to indicate failure. So non-zero exit values indicate failure. So the problem, what's the problem with this? Well, I guess I should say it. We're throwing out the return value though. So we need to keep track of the return value to know how many bytes we actually read. That's what this value here is supposed to do. So to fix this, we can actually jump back down to here and say bytes read equals read. Then we can wrap this all in parentheses. And this works because in C, assignments are actually expressions as well, and they just return the value that was assigned. So here we're combining all into one, saying bytes read equals the result of read, and then check if that's -1, and if it is, handle the error. Now we want to print the result of calling what was stored in buffer, what was read into the buffer. So we can do this using %s \n buff. Now let's try running this. And we'll say read underscore file. And we'll pass readfile.c to this file. And you'll see we get some garbage output here. Does anyone know what the problem is? Because it's all normal up to here. Then it stops working. Can anyone guess what the issue is?
This is just a guess, but is it that we haven't specified what like character encoding format the file is using?
Good guess, but not quite. No. Yeah.
Is there like an invisible character turn in there that's misreading?
Not a character term, but it does have to do with a character that we can't see that's missing. So you're getting closer.
There's no null character to terminate this.
Exactly. There's no null terminator. So remember, strings in C are really just arrays of characters, and if there's an array we want to be able to perform operations on without knowing its length ahead of time, the convention is to end that array with a 0 character, \0 in single quotes, the null terminator as it's called. But we didn't do that with read. The read syscall does not do that for us. It does not append that null terminator to the buffer. It just reads the number of bytes given to us, or that we specified, I should say. So for us, we can't use %s because %s will read until it encounters that \n character. Or not, I'm sorry, not \n, the \0, the null terminator. So printf just printed characters until it reached, past the point of what it should have printed, basically. So to avoid this issue, we're going to have to manually print each character individually. So we'll say for I equals 0, I is less than, and I'll declare I here. I don't think I did, I did declare there already. Okay, so I'll just say I equals 0, I is less than bytes read, ++ I. We'll say printf %c buff I. And now if we run this, readfile.c, we can see that we get no errors this time. It just stops. And the reason why some of this was probably messed up in the past is because we probably printed characters that were backspace characters. You can actually print a backspace character, and that will affect how the output looks. So we had messed up the whole output by using the %s specifier, as opposed to actually printing the characters one at a time. So this is the correct way to do it when you're reading with the read syscall. The alternative is to just append a null terminator manually ourselves. We could have just said buff 31 is equal to 0, and then we could have used %s and it would have worked, but we would have lost the last character that way. So this way we're able to make use of all the characters in our buffer without needing to use an null terminator. Okay, any questions about read? Okay, so let's go to, let's see, what else do we have here? Yeah, write. Yeah, we'll go to write next. Okay, so in this example, probably gonna, I'll maybe leave that, okay. All right, so in this example, we're doing something similar as before. We're creating a program that accepts one argument, and it's going to write the string hello world to that file that was passed in at the command line to this program. This is called writefile.c. So the binary is going to be called a writefile. So we're going to open this path, the argument given to us. We're saying the first argument is going to be stored in the path variable. And we're opening it. What does owriteOnly mean? We're only going to open the file for writing. What does ocreate mean?
Create file if it doesn't exist.
if it doesn't exist. And then what does O trunk mean? What? What? Yeah. Basically, delete everything in the file before we start writing. Truncate it, delete everything that already exists, basically. And then these, what do these last set of flags specify?
Permissions?
Permissions, right? You don't even know exactly what they are, they're just permissions. I guess one small thing, you can actually specify permissions like this in octal format really concisely. The only drawback to this approach is that you need to be able to read permission specifications in octal. You don't have groups available, or symbolic constants available to you. It's actually not that hard to read the permission specifications. I can kind of give a brief rundown of this right now, actually. So if we have a permission spec, let's see. Read is always going to be 0 or 4. Write will be 0 or 2. And then execute will be 0, 0 or 1. And if you want to specify permissions in octal, what you would do then is say the user permissions, group permissions, other permissions. And if we wanted to specify, for instance, read permissions for the user, you could say 4. Write permissions for others, you would say 2, and or for the group, and then execute permissions or no permissions for others, you could just say 0. And then the way you can actually specify more permissions is by ORing these values together. So 4, or adding them together, I should say. So if we said 6, it would be read plus write. 4 plus 2 is 6. We would say read permissions on the user, read and write permissions for the user, write permissions for the group, no permissions for others. This is kind of how you would be able to read the permissions for in octal. Yeah, again, not really necessary. You can just use the symbolic constants. One that we'll often use in this course is just 644. What that corresponds to is read write for the user, and then just read for everyone else. So we'll do that here actually, just to show that it works. 644. So what this will do is just create the file with read and write permissions for the user, and then only read permissions for everyone else that tries to access the file. So here we're checking for errors. And then the write syscall behaves similarly to read. Oops, that's the write command. Where we're going to specify a file descriptor that we're writing to, a buffer that we're writing from. So now the buffer is their source, not the destination, and the number of bytes that we're going to be writing from that buffer into the file descriptor. And the result is going to be the number of bytes that were written. So here we're checking if -1 is equal to bytes written, that means there was an error, so we return early. And then we say, you just close the file. So I'm going to skip this commented out block for now. I'll run this write file.c, and we'll create a file called hello.txt. And you can see there were no errors. And if I look in my current directory, there's now a file called hello.txt. There should be one right here. I can cat out its contents, and there exists a file called hello world, or that says hello world. And if I run the stat syscall, you can see that its permissions are 0644, read write on the user, read on everyone else, and that corresponds to what we had passed right here. So if you don't want to use the octal numbers for permissions, you don't have to. You can just use the symbolic constants by checking the man page to open. Oops, wrong one. Somewhere down here. Yeah, you can just use these symbolic constants instead if you don't want to use the octal numbers. But if you feel comfortable, you're fine. You can go ahead and use them. Okay, so any questions? Yeah.
What stops a program from trying to access, trying to write to it by saying, I'm a user.
So the user is going to be the same as the owner. Sorry, I should clarify that. The user permissions are for the owner of the file, the one who created the file originally. Yeah.
Gotcha.
There are ways for a program to change what their permissions are when they're running, but usually this is for system binaries that the root should be run by the root or should be installed by the root. So they're not ones that are known to be compromised. It should be safe to run. Yeah. Okay, so one more thing I want to show with write is that the write syscall can be stopped prematurely if a signal was sent to our process while it was running, our program while it was running. And for example of what a signal could be, I think I've shown this before, Control Z is a signal that I can press Control Z to send the stop signal to my editor while it's running, to put it, pause it, basically. And I can press FG to resume it. Now we could actually, if our program took a long time to run, if I wanted to write like 1,000,000 bytes, when it was taking a while to run, I could press Control Z to stop the process from running, and then it would stop at that point, and write would only return the number of bytes written up to that point, maybe like 500,000 bytes, which wouldn't be everything we wanted. It wouldn't be done running. So to protect against the case in which a program stops before it is done writing all the bytes that it is supposed to write, we can actually set up a loop like this, where we record the total number of bytes that we've written so far as bytes written, and then we can check while bytes written is less than the count, the number of bytes that we want to write, which we'll assign to the length of this buffer itself, the length of the string that we're trying to write. Then we just iteratively increment the number of bytes written by the call to write. This should be total bytes written is plus equal to write. And here we're actually doing some pointer arithmetic to go past the number of bytes that we've written so far to write the number of bytes that we have left. So the total number of bytes to write minus the number of bytes we've already written. We're going to write that many additional bytes to the file descriptor. And then in the end, we can actually print the number of bytes written with this call to printf here. And see that we have to use the Z specifier. We can actually look at the manual pages for size types, size types, and they tell us right here the length specifier for size type for printf and scanf families is Z, resulting commonly in ZU or ZX for printing size T values. So, and it says here for size type, Z works for size type. It's not quite portable. We'll use it instead. We'll use it anyway. So, ZD for signed size types. If it was unsigned, we would just use ZU, but we're using ZD for signed size types. So if I run make again and run write file.c, hello.txt, it actually will tell us now number of bytes written was 14. So we know the file's length should be 14. So if I run file on hello.txt, stat on hello.txt, it'll tell us that it's 14 bytes in size. Okay, any questions on the write syscall? You won't have to use this one too much in this course. You will have to use definitely the next set of syscalls, though, that we'll be reviewing, which is the directory syscalls. Now, these are not actually syscalls. These are actually library calls. They're a bit higher level and easier to use. We're going to be using the library variations of these functions because the syscalls are pretty low level and they're not really easy to work with. So in this course, we're going to be using these three syscalls for opening and navigating directories. So this will let us open a directory and then walk across the files in the directory and then eventually close the directory. So I think that is, directories.c. So when working with directories in C code, the first syscall we want to use, and what this program is going to do is accept the directory as an argument. The first syscall we're going to use is opendir. This is actually, again, a library call. It opens a directory. It expects the name of the directory as its argument, the path to the directory. and it returns this dir pointer. Opens a directory stream corresponding to the directory name and returns a pointer to the directory stream. The stream is positioned at the first entry in the directory. So return value, open dir, and its other variation, return a pointer to the directory stream. On error, null is returned, and error no is set to indicate the error. So we declare our own pointer variable up here, dir pointer, dir p, and we assign it to the result of open dir. And if that's null, then we p an error, print error, and then exit. Now in this second block of code here, we are actually walking the directory tree. So once we open the directory, we can call redir to return a pointer to a directory entry structure, representing the next directory entry in the directory stream pointed to by dir p. It returns null on reaching the end of the directory stream or if an error occurred. So this is essentially, what does this look similar to? While this is not equal to null, we walk through this list. What is that similar to? A linked list, right? So again, concepts you see in previous CS classes are coming up again in this class, in this course. So the way you walk a directory using these library calls is the same as how you would walk a linked list. So while this redir does not return null, this is the same thing as saying this. It's just that in C, null is a false value, so I can just write it like this, and that's the same thing. While dirent equals redir, and you can see that redir returns null when it reaches the end of the stream, or if an error occurs. So since redir returns null both in the case of an error and in the case of reaching the end of the directory without throwing an error, it returns null in both cases. The way that the manual tells us to distinguish between these two is to set error no to 0 before calling redir and then checking the value of error no if null is returned. So that's what we do in this loop here. We set error no to 0 first, then we read through the directory entries in this directory by repeatedly calling redir until we get null, and then checking for 0 afterwards. And then we can determine what fields are available to us in these directory entries by looking in the man pages again, and we see that it gives us the name of the file, the type of the file, the inode number. One thing to note is that this name is not the full path to the file, it's only the name of the file in the current directory. So for your myfind project, you'll need to get the full path to the file, and you'll have to do some path manipulation stuff to get that. But each directory entry struct here only gives you the name of the file in the current working directory. Yeah.
What does your not equals symbol look like that?
Oh, I have a font installed that has what's called ligature support. So you can look up a font. They're often called nerd fonts. Yeah, fonts that have support for ligatures. That's the word you want to use. If you can download one of those fonts, then when you type in characters like not equals, if they're together, it turns into a special character. So kind of cool. There's a whole bunch of them, like this, this. Yeah. Okay. So also arrows, which is cool for when you're doing stuff with pointers. All right. So anyway, so we read the directory entries, then we return 0, and then we call close dir, which, as you might expect, just closes the directory stream. So like we have close for opening files and closing files, I should say. We have close dir for closing files. Now with all these, if I run make, and then call this directories program and pass it the current working directory, what do you think is going to happen? What are we doing in this code snippet here? What?
It's printing the name of each directory.
Each directory entry. So that's each file in the directory. Yeah. So if I run it, you can see it actually prints every single file in the current directory. Notice that it also includes dot and dot dot. So in your myfind project, you'll want to exclude those. So you'll have to check using string comp or something similar the name of the file to see whether or not it's the current directory or parent directory. Okay, so I think we're almost done. Yeah, 2 last syscalls. These ones are pretty short. We have the link syscall. What do you think the link syscall does? Yeah, it creates a link. Now, it creates specifically a hard link. So, what's the difference between hard links and soft links? Can anyone remind me?
Soft links, the metaphor of it being like you have a tunnel to the information or the data, but with a hard link, it's like the same place where the data is, so you can manipulate more with soft links.
Yes, exactly. So a hard link is like installing an extra door on your house, where the house is the inode, and a soft link is like creating a tunnel to that house, where the tunnel has its own separate inode. So if you delete the extra door in the house, delete one hard link, as long as there's another hard link there, another door, the house still stands, you can still access its contents. Whereas with the soft link, if you delete the tunnel, the house still stands, but the soft link is gone, and if you delete the hard link, all the hard links to a file, the house, then the tunnel leads to nothing, it becomes a dangling link, and it no longer accesses anything, any file. So with this link syscall, we create hard links. There's also another syscall, I believe, called, I think it's just called symlink, which lets you create soft links. But we'll be looking at just link here. So again, same process as before, we accept one argument, or in this case, 2 arguments from the user. We assign them to these 2 variables here, and then we call the link syscall to create a soft link, or a hard link, I should say. And let me open up the correct man page here. It says that the first argument is old path, the second argument is new path. So presumably, the second argument is going to be the name of the link. So let's try this out. We'll run make, run link, and we'll we'll pass this hello.txt file that we created earlier, and we'll create a file called hello hard link.txt. And now if I type in ls, you can see, let me actually do this differently, ls-i1 to print inode numbers and to print each entry on its own line. And I'll just get the inode numbers for hello.txt and hello hardlink.txt. And we can see they had the same inode numbers. So it seems like the creation of the hard link was successful. So if you don't know the flags for ls, you could have just ran stat on both hello.txt and then stat on hello hardlink.txt, and you would have been able to compare the inode numbers from here and see that they're both the same that way. So in any case, it seems like the program worked. And now we've implemented our own ln almost at this point with just this very simple C program. 25 lines of code long. So that's kind of cool. Okay, now for the last syscall, any questions about the link syscall? This is just to give you a lot of examples of how syscalls work. The last one is rename. This one's pretty simple, pretty similar. The rename syscall, as the name suggests, takes an old path and then a new path and then renames the old path into the new path. Renames the file, moving it between directories if required. Yeah, so this is actually how the move syscall is probably implemented under the hood. Or move command, I should say. So in this case, let's try running this now. So make, we'll say rename, we'll pass that hard link we created. Hello hard link, hello hard link renamed.txt. And now if I cat out the contents of that renamed file, it still has the same contents as before. And if I, let's go back up to my previous command where I ran ls. Oh, it's not here. Probably it was in my other window. ls-i1, hello.txt, hello hardlink.txt, hardlink renamed. You can see it still has the same inode number as the original file. So I encourage you to explore these syscalls and maybe experiment with a few of these ones we saw today. These are some of the most common ones you'll be using. And yeah, get ready for the MyFind project, because that's the first actually challenging project that we have in this course, and it will require you to use many of the Syscalls that we saw today. So if you have any questions, you can ask me now or wait till office hours. I'm going to end the recording now.